Everybody, and thank you for being here for this second webinar of our 2024 series with RegionU. And as always, I would like to thank our speaker, Johan Ulrik Lind, to be here today. Hello, hi, Johan. And I will give a brief introduction of him and give you some quick technical info about the event before I leave him the floor. So for what concerns the event, we will have the talk, and after we will be open for a Q&A session with our speaker. Of course, I invite you even during the event to pose any question you may have through the chat tab or the Q&A tab of the Microsoft Teams application. And so I can start by introducing our speaker. Professor Johan Ulrik Lind is Associate Professor and Group Leader for the Tailored Material and Tissue Group in the Technical University of Denmark. And his research is centered on merging tissue engineering with material engineering for the fabrication of in vitro models of tissues and organs, and for the fabrication of biohybrid implants that can embed soft biocompatible electronics, soft sensors, or actuators within the engineered tissues. So it's a pleasure to have you here, Johan, and I leave the floor to you.
Okay, thank you, Mauro, and thank you for tuning in, those of you tuning in here. So I will just see if I can share my screen here, and hopefully you can all hear me and see me. All right.
Yes, we can see the in presentation mode.
Okay, excellent. So thank you, RegionU, for the invitation. I'm thrilled to share a little bit of the research that we do in my group in northern Copenhagen here at the Technical University of Denmark. So the title of today's talk is Towards Multi-Material Printing of Biohybrid Tissue. So the towards kind of indicates that this is an ongoing process, and obviously a topic that many groups around the world is interested in. And by biohybrid, what I really mean is that we're talking about tissue models that are somehow merging artificial and living matter. Okay, so the overall kind of vision that we're working towards is different ways of engineering human tissue and merging that with different ways of creating functional materials. And quite, we believe, and many others do, that multi-material 3D printing is a unique opportunity for building such hybrid tissues. And in terms of application areas, what we're really focusing on is instrumented tissue models for in vitro biology. So that could be drug development, but also disease modeling purposes. But more recently, we also are moving into the in vivo space. So what I will really focus on today is a collection of examples and focus on considerations around ink design. So obviously, designing inks with specific fluidic or printability properties is one side of the coin. The other side of the coin is that when we're talking about functional materials or biological materials, we also want those inks to have certain functionalities. And so I'm gonna give some general thoughts about how we use different types of ink design for different applications. So here's an outline of the talk. So I'm gonna give three overall kind of example areas. So one is cell-instructive prints and print materials, a little bit about ink fundamentals first, and a collection of different examples. Then I'm gonna focus on soft electronics. Again, a little bit about how we attack that problem in terms of formulating inks, and also some diverse examples. And the last example is our work within embedded bioprinting, which is obviously a topic that many groups are interested in right now. Okay, so cell-instructive prints and materials. So if we start with the very basic ink fundamentals, as most of the audience probably knows here, traditional bioprinting really focused on the formulation of shear thinning gels, foams, and pastes that have a well-defined yield stress that makes them flow under shear. And I always tell my students they can think about toothpaste as a good example of such a material. And obviously, to get these properties and also recovery after extrusion, then you really often need to have some kind of weak or reversible bonds and or some post-printing solidification, so cross-linking that could be UV-based or enzymatic or whatever. But we can also play a little bit more with the formulation of these materials. So one classical example that we will return to here is like this, what some people call 4D printing, where you use the printing process to induce some kind of organization within your printed material. So this example was one of the first, where embedded cellulose fibers direct the swelling properties of printed patterns. So when you print a pattern, swelling in a liquid will be controlled by the orientation of the fibers. And that's a principle that we have since adapted for biology. So, cell-instructive printed materials, the examples that I'm going to show are towards striated muscle. So striated muscle will be skeletal muscle and cardiac muscle. And they have several features in common. So obviously they're both striated, and they are both very highly anisotropic. So all the muscle fibers in striated muscle pull, at least locally, in the same direction. So if you want to build any model of those types of tissues, you need to recapitulate this anisotropic organization. Then, of course, they are contractile, so they shorten. So you should have some kind of environment that allows the muscle fibers to shorten, and they also need to be coupled, electrically coupled through gap junctions in the cardiac tissue, or fused in the case of skeletal muscle. So when I entered this field, the first approach that I took was to apply traditional extrusion of highly shear thinning silicones as a way to organize tissues. So if you have a small enough needle and a good enough printer, then you can, of course, print small grooves of, say, 60 micrometer in feature size. And that's sufficient. Let me stop this video from turning for a second, for organizing the orientation of cardiomyocytes. So if we stop the video here, boom, then you can see that hopefully you can appreciate for this picture that along these grooves we get an anisotropic organization. If not, it's more clear here probably that you can see all the sarcomeres. So that's the contractile units of the cardiomyocytes. They all pull in the same direction. And that is obviously very dependent on the geometry that you print. So if you have no features here, then you get very isotropic tissue, and there's a trade-off between the spacing and the feature size here that you can play with in your printing. So equally important to the contractile units being organized as it is in the body, you also need electrical coupling. So we studied the electrical coupling of tissues cultured on these groove substrates, and found that that in addition to a contractile anisotropy, you also have electrical coupling, so that the electrical signal that is inducing the contraction of the tissue is approximately twice as fast in the long direction as across the grooves, which matches what you see in vivo, or these ex vivo tissue sheets. So that means that this kind of relatively simple approach, you print some grooves, you seed some cells, is quite efficient in matching native biology. I will return to some applications of this later. But let me focus a little bit on the fabrication here. So the main downside of printing very small features on an extrusion printer is that our printing time is obviously proportional to the length of the path that we move. So if we print small features, moving the needle back and forth in small steps, then printing takes very long time. So one of the things that we've studied in my group over the last couple of years is whether we can somehow get around this problem. So the first study we did was on spontaneous self-organization. So, and now we're switching to skeletal muscle, but the same principle applies for cardiac muscle. If you culture skeletal myoblasts, then you fuse them into skeletal muscle fibers. So these are muscle fibers that you can see here. If you just culture them in a regular petri dish, what you see is that you get localized areas where the fibers are pointing in one direction, but overall it's randomly organized. So if you kind of zoom in very locally, you have a high alignment score, but if you go out broadly, then you have random alignments. That's also true if you culture cells on soft gels. You get some kind of local domains that are highly aligned, but overall you don't have any control. But what we observed, and this was actually just a small bachelor project, was that if you go into sufficiently small, soft and viscoelastic substrates, then these domains, they increase in size. So this is the same culture, but only if you go extremely deformable, then you start to get high degree of universal alignment. This is obviously random, so we don't control it, but we can at least use this as a tool. So we were interested in saying, like, if we now use these soft materials here, can we get away with just very small cues? So rather than print features that are, say, 60 micrometers in size, we were interested in studying if we just print alternating patterns of different mechanical properties of gelatin, can we induce this overall organization of the skeletal muscle fibers, but without having to go very small in feature size. So essentially, we were studying what happens when we print now in steps of hundreds of micrometers and big filaments, which is obviously a lot easier and more scalable to do. So we essentially relied on very common gelatin inks that you can, of course, melt, has a well-defined melting point. Post-extrusion, it gelates, then you can cross-link it. In our case, we used the enzymatic cross-linking. And then we coupled a stiff substrate with a softer, lower concentration gelatin, where we then print filaments of the soft materials on top of the stiff material. And to get better fidelity, we added a little bit of xanthan gum, so a viscosity modifier that increases the viscosity of the gelatin, commonly used. And you can see here, when you add this to the soft material, then you get more well-defined lines that you can space closer before they start merging. So in this case, we have merging quite rapidly if you don't add the xanthan gum. So this is just like a small trick. And then what we found is that on these crudely patterned substrates, so 400 micrometer spacing between each line, so that's about 0.5 millimeter, and relatively big filaments, we can get very universal alignment. And this obviously takes a lot less time to print than these microscopic features. So we just play with the mechanics of the material, and then we let the tissue essentially do its work. But what you can probably see here from this picture, or at least I'll show you in a bit, is that there's a little bit of an angle here, and that's an issue. So, and even so, maybe I should finish that point, but even if you go to, say, 600 micrometers, you can still appreciate that you get a relatively good amount of control, and you only lose it if you go beyond 1 millimeter. And if you then if you compare these skeletal myoblasts on these pattern gels, what you see is, as compared to regular tissue culture or just unstructured gels, we get better organization, we get longer myotubes, so in the order that are typically like up to 1 millimeter in size, so that's approximately 10 times larger than you typically get in conventional bioprint. And you get a better fusion index, so more of the cells will participate in the myotubes, and you get over time, you get nicely well-defined sarcomeres resembling native tissue. Okay, so what we observed was that in these, while we can get very nicely aligned myotubes using these crude patterns, we always observed that these come at an angle, and this was extremely robust. So that means that if you print circles, a circular pattern, then you actually end up with a spiral. So this is just color-coded for orientation here. But you can appreciate that the myotubes, they actually follow a spiral, even though the print is a circle. So it looks beautiful, but we would like to be able to have a much tighter control of the organization. So then we turned to what I showed in the beginning here, whether we can use anisotropy within the print material as a guiding principle. So cellulose nanofibers has been studied a lot, obviously, as an additive for extrusion-based printing and extrusion-based bioprinting, and most formulations are non-transparent. So if you get microfibrillated cellulose, your prints will look white. And that's a problem if you do a lot of microscopy like we do, that we would like to be able to visually assess the cells easily. So the first challenge here for us was to formulate some nanofibers that remained fibrillar, but were transparent. So what we turned to was a very classical reaction, which is carboxymethylation, where you carboxymethylate the side chains of the cellulose. And what that does is it makes it more hydrophilic. It also kind of etches down the size of the fibers. So as we increase the degree of reaction, we get an average fiber width decreased from, say, 350 to about 250 nanometers. And the way we tune that's kind of a detail, is actually by the choice of solvent instead of the reactants. We found that to be more robust. And what you can see is that, okay, the fibers, they become smaller, more dispersible, and they become more transparent, but obviously they are also not as good as print material. So luckily you can fix that by playing with concentration. Essentially, you need to, of course, get some kind of entanglement of the fibers to get nice printable rheology. So by increasing the concentration, we can now get, very well-defined prints that are optically transparent, at least transparent enough that we can look at our cells. So that means that the octopus I showed you in the beginning, we can formulate that in a more transparent version. But now to the cells. So then we were interested in seeing, like, okay, we know that these nanofibers should align with shear as we print. So essentially, we put the fibers in into the gelatin inks I showed you before. And what that means is that the local stiffness will be different along the fibers and transverse to the fibers. And what we found is that that was very efficient in aligning the cells. We get beautiful skeletal myofibers. We can culture those for months. And what we can also see is that they follow very well local orientation. So if we print them in a checkerboard, we will get orthogonal orientation in the checkerboard areas. And if we print a circle, now we get circular patterns and not spiraling patterns. So now we are kind of using this for different applications. I'm going to show a few later in the presentation. But obviously, you can use the same fibers also in traditional bioprinting. But there is some limitations for how high concentrations you can go here without getting into shears that will damage the cells. Okay, so now to the second part of the talk, and I'm going to try to merge these topics as we go along. So we also have a parallel activity about soft electronics. So when we think about printing soft electronics, we really like to work with dilute thermoplasts. So essentially, the inks that we're applying now are not traditional shear thinning inks, but they more behave like nail polish, that we have volatile solvent that evaporates as soon as you extrude it, meaning that you get a very rapid increase in viscosity, and that prevents flow. So this is a technique that is really, really good for printing thin films. And the first example that I want to show is some of my old work from my postdoc, where we essentially stacked these several layers of thin elastomers and thin electronic materials to create a hard-on-a-chip device where we have, in this case, these small microgrooves for organizing a tissue, anisotropic tissue. And those are then cultured on top of a thin elastomer with an embedded strain gauge where we can record the contraction of the tissue. So the way it looks is something like this. So by having these dilute inks that solidify as soon as you print them and working with very close distances to the printer, you can print films that are easily in the order of microns. So down to single microns is not too difficult. So obviously you can't do high aspect ratio features, but what you can do is they can stack very thin films, which means that they are very deformable for bending in at least one direction. And then we add these grooves on top that I showed in the beginning. So this, you can see these grooves being added here on top, taking a lot longer time than just printing the cantilevers. You can incorporate that also with some printing of some housing, and then you have a fully printed device that takes about an hour to print. And what can you use those devices for? Yeah, you can study, of course, development in contractile force that we record from the resistance. As the tissue matures, we get an increase in contractile force as the stem cell derived tissue becomes more and more mature. Let's plot it here. You can see changes, a decrease in spontaneous beat rate, which is also expected to decrease as the tissue matures. And this is obviously reflected in microscopic changes. So in this case, I plotted the sarcomeres. So you can see that the sarcomeres becomes more and more oriented, and they also become longer and longer. Both are signs of a more mature tissue. And we also demonstrated that you can use it for non-invasive drug studies. In this case, I'm just showing two, but we did several as a platform for non-invasive studies of human tox or long-term responses to environmental factors. One of the things that wasn't ideal with this system that I'm showing here is that for thermoplastic polyurethanes, you typically rely on polar solvents that tend to have a high toxicity. So that would be something like THF or DMF as a carrier solvent. So we were interested in looking at alternatives. So since then, we focused on two things. So one is to get rid of the silicones. We're focusing on polystyrene-based inks. So we're doing that now for printing PDOT-based electronics and incorporating those in polystyrene dishes, you could say, using for electrical pacing of cells or multi-electrode arrays for recording cellular signals in vitro. But we have also focused a lot on SEPs. So SEPs is another thermoplastic elastomer. But as compared to the polyurethanes that we used before, we can dissolve this in much more benign solvents. So we still apply this nail polish rheology, you could say, to print thin films, but we can also print freestanding features by going into a more high viscosity domain. So just one couple of examples. So we're exploring those for different types of sensing. So obviously dependent on the what you add into your composite. So if you add silver particles or carbon black or PDOT, this is an organic formulation of PDOT, you get different conductivities, but you also get different sensing properties. So one thing that we observed was that we were interested in exploring whether any of these composites could be used for sensing variables. So obviously strain gauges is an easy use, but we were also interested in seeing, like, can we record something like temperature? So we studied the response to temperature sweeps of these system. What we found was that our PDOT system was very insensitive to temperature changes. So that's kind of interesting. And that our carbon black particle-based system was very nicely reversible in responses to temperature. So we are exploring that now for uses for wearable sensors. So here's another example of the same system being printed on top of textiles. So these are now, we explore those as uses for real-time monitoring of ECGs of individuals through these printed electronics on textiles. And here's a couple of examples where we record that. Okay, so the last example I will give of our recent work is embedded bioprinting. So it's a little bit of a different direction. So obviously embedded bioprinting has become very popular in recent years. And one of the reasons is that it overcomes the fundamental problem of cell viability, in that to get very nice printability, we typically work with high viscosity liquids, and that yields high shears, meaning that there's an inherent trade-off, I would say, in traditional bioprinting between cell viability and phenotype preservation, if we're talking about stem cells, and the spatial resolution that you can get. And embedded printing is, of course, the most popular way to get around this. So you print into a support, and I would say the vast majority of studies in recent years has been on jammed microgels as a very biocompatible support for printing in your bioink. So when we started looking at this, one of the things that we were interested in is whether we can formulate supports that promote cellular outgrowth. So one of the things that goes into that is, can you give a lot of space in this system? So if you have jammed microgels and those gels are cross-linked, then you leave the cells with limited space for outgrowth. And the other thing we were interested in is whether we can make a system where we can vary the ECM composition that surrounds the cell quite easily. So this was a collaboration with the engineers and was led by Janko, who's the first author of this paper. So the idea was as follows. So we take one of the granular components that are commonly out there and optimize a little bit of that. So in our case, we focused on alginate. And then we were curious if we then, instead of jamming the particles into a low viscosity solution, we were interested in, if you add a continuous component here to the granular gel where you have high viscosity solution here, then we might be able to get more space around these gels, microgels, and use this component to control the ECM. So we were interested in studying, or we studied in this case, neurons, and we're interested in seeing whether we can have a system where we can simultaneously promote growth and outgrowth of axons from the neurons. in situ. So we studied mainly collagen and alginate here. And then we also studied whether we can use it for making perfusible channels for vasculature, etc. So first, for the basic principles. So if you print into a nicely jammed microgel here, you can print nice features here with a high spatial resolution. If you then start to dilute it, like you add a little bit too much media, you could say, around the microgels, then you lose this spatial resolution. And what we found that if this continuous component in between the microgels is of a high enough viscosity, then you can still have a higher spatial resolution, but now you have more space for the cells to grow into, and you have a better control of what this environment the cells are growing in and looks like. So here's a couple of examples that you can get nice spatial resolution, and you can also do all kinds of different components between these microgels. So in this case, we showed a couple of different ones. But what's interesting, of course, is when we're now doing better printing in these composites of alginate and collagen, where about 1/3 of the volume is essentially a collagen-based matrix, we now can see cellular outgrowth, and we can have axons that grow up to millimeter distances from where they are printed. That means that we can start compartmentalizing, printing different types of neuronal tissue, and have connections being formed in situ between those, rather than so in a soft environment that mimics the native brain, you could say. And the last thing we looked at, which is primary focus right now, is also doing vasculatures, perfusible systems that can then be combined with these printed neuronal tissues. So that's, you could say, ongoing research. Okay, so this is most of the people that did the work from at least 2023, our small group. And this is all the people that contributed and all the funding that helped support the research. So I think that wraps up my presentation. So thank you for your attention. I'm happy to take any questions.
And thank you for the wonderful talk. Now we will open for the question. I remind everybody that if you want, you can write them in the chat or in the QA tab, and we will tackle together with our speakers. So if you don't mind, I will start with a couple of questions on my side. So first of all, I would go to the electronic parts. I had a couple of questions on that. First one is if you can provide any info on the amount of let's say conductive or microparticles that you can put in your ink and the granulometry without then having issue for what concerns the clogging of the nozzle, the printability issue, and the
yes, excellent question. So let me see. So I probably should share again. I'll switch back and forth, I guess, so I can also see who's asking. So so if we look at the SEPs, for instance. That would be, I think, here. We looked at how much volume content of filler. So in this case, the filler here is the conducting particles. And when I say volume, this is the volume of the final composite. So remember, in these nail polish based inks, there's a large fraction of carrier solvent. So we start out by making, say, a 20 volume% solution of the polymer, and then we add particles to that. And then in the final composite, we can easily get up to, so this is for silver particles, we can easily go, here's plotted up to 40%, and we just look at the conductivity. You can obviously get higher. We can get at least up to 60% volume fraction of conducting particles in this particular system. But you get less bang for the buck, you could say, in terms of you get the increasing conductivity every time you increase the amount of particles loaded, but you also it's more expensive, you could say. The silver is expensive. But then there's also the mechanical properties. So I didn't include the data on this slide, but obviously, as you add more and more filling to these elastomer inks, we decrease the stretchability of the system. And that's very much dependent on the type of particle is what we found in this study. So, for instance, for this subspace system, which has been published actually quite a bit using other approaches, we found that the silver composites were significantly more brittle than, say, the carbon black particles. And that's also true if you add graphite particles. And that kind of highlights in our view that the binding between the particles and the matrix is key. So so you can of course work with the compatibility of the silver, but we found that, for instance, silver composites with thermoplastic polyurethane was more stretchable than SEP's composites were. And the same was actually true for PDOT. So we actually anticipated the PDOT composites to be the most stretchable. We found two things: we needed to add more to get a decent conductivity, but also they actually compromise the stretchability the earliest. So I would say, in terms of how much you can load, let me unshare again here. In terms of how much you can load, I would say we typically can go up to like 60 or 70% of volume in the final ink. So that's quite high, I would say. So only 30% binder, but you compromise stretchability typically, which is something we're interested in. And obviously, it's easier to, these are quite dilute. So the main thing that you're working against is actually sedimentation in terms of clogging. So you can avoid sedimentation completely to go to high concentrations of polymer, right? Increases the viscosity of the system, but that also means that then you are restricted in terms of extrusion. They become very viscous. You need to use big nozzles. So we found, and that's detailed in the paper, that a good compromise for us was in this 28% solutions of this particular polymer, but it will be polymer dependent.
Yeah, no, absolutely agree. And then I suppose the goal is always to minimize the particle concentration whenever it's possible, as long as electrical conductivity is preserved for mechanical sustainability and release reason and whatever.
Yes.
And instead, speaking of the carriers, have you ever considered or tried that some experience in using, for example, instead of solvent-based inks, electrospinning or electrowriting opportunities? For example, for the thermoplastic polyurethane, it is compatible with melt electrowriting. It's an approach that you had some experience.
It certainly is. It's not something we have done. I mean, I think there's some challenges in terms of the composites. I mean, it's not trivial, at least. But for the pure elastomers, you're completely right. That's been done. I think it's interesting, and I think it's good that other people are doing it. But it's not something we're focusing on that much at the moment in our lab. But I mean, they are thermoplastics, so you certainly are right. And you can also, obviously, you can use high temperature printing of these composites also. If you don't like to use the solvents, you can melt them on a high temperature melt head and print at least most of these composites. But we have found that for many of our applications, we like to have this, that the fact that they are thin is important, because that means that they're bendable and flexible to the biological tissue. And for that, we have found that it was easier for us to use a carrier solvent. But you can also print the same materials. If you're fine with bigger features, you can load them and remove the solvent in a high temperature printer.
That's why I was considering electrowriting, to preserve the flexibility and the thin fibers.
Yes. And I don't know. It's a good question. Yeah, somebody with more experience in electrowriting would tell me how much the particles would challenge that. But
for sure,
in principle, I say, well, would you be short-circuiting the system right away? There might be some. There might be at least some challenges there, I think.
But certainly, there is a room for research.
Yes.
And then, if you could spend the last question on my side, I promise, a few more words on the tissue modeling part. So, in the end goal of application, have you also tried some drug testing? What's the goal? Disease modeling? What?
Yes. So here in this presentation, I focused very much on principles of printing. We tested in similar platforms something like 20 cardiotoxic and or cardiac drugs. So not necessarily cardiotoxic, but we definitely verified that you can use these for drug screening, and we also used it for studying ischemic heart injury, where we take advantage of the fact that if you incorporate sensors you can change the environment. Like if you have an optical sensor, then you typically need optical access. And for instance, if you want to record real time in an ischemic environment, it's convenient that you could just need a wire to record how the tissue is responding over time. So we took advantage of that to study ischemic heart injuries, and that's in a different paper from 2021. But you could say that one of the things that we and many others are focusing on right now in terms of diseases, traditionally, disease modeling in vitro models have very much been genetic disorders. Okay, you take a stem cell line, and now it has a genetic disorder, and does it behave different than the control cell line? And usually it does. But I think what we and many others are trying to look at now is more environmental factors, which have been harder to mimic, right? So can you make a diabetic heart, for instance? Yeah. That's not trivial, but it has a very big clinical relevance, you would say, whether we can mimic those processes, and those are typically longer processes. So that means that we need to have systems and models that are compatible with very long-term culture.
Okay, yeah, I see. That's of course one of the main challenges right now on this. It's really a different kind of application. And what about just a quick curiosity, the fabrication time for this neural model that you showed us with embedding? Because if you want to move to testing,
relatively fast. I mean, the fabrication time in itself is like less than half an hour, I would say. But the preparation time is usually the trick here, right? So so we're trying to streamline that a little bit now, and so because you need to have a bubble-free support bath that is and needs to be loaded with collagen that's temperature sensitive. So there's some practical stuff that luckily my PhD students, were dealing with, but the fabrication time and the print time is not really an issue. Like I think that's yeah.
I agree with you. Generally, is not really the fabrication time the bottleneck, as many people may think.
Yes, yeah, certainly.
So I have a question from the audience. Let's see. So Cesare, thanks you for the outstanding presentation. And he has a question about on which tissue models you were planning to implement vascularization. And another small question about the thickness of the last model you presented.
How thick is the model you presented on the last slide? So, okay. So we are working, we're collaborating with the group that I did the neuronal work with. We're for continuing that work to vascularize neuronal tissue. And then my group comes from a cardiac tissue engineering space. So we're also looking at that. And then we are also early stage exploring intestinal models based on these principles, obviously, also. So that's not vascularization, but other perfusible tissues. The last slide, I'm trying to, should I make sure that I know which tissue that is being referred to, but I would say in general, the thicknesses of the tissues were in the orders of, say, hundreds of microns, but embedded in gels. So quite small and also relatively low cell densities. So if we go to very high cell densities, obviously without having the perfusion figured out, then we run into problems with nutrition and supply. Yeah. It was the perfused one. It says, okay, maybe Cesare can. And the channel sizes that we can do are filament sizes, so hundreds of microns right now. Good. I can see that Cesare is writing. Okay, I think I answered the question, I hope. Otherwise, you're welcome to contact me.
Yeah, of course. So then I will say we have taken quite enough of your time already. So I would like to thank you for the wonderful talk and the availability to tackle any question. And I remind to every participant that if they want to they come with more questions, they can directly contact you or us, and we will certainly be glad to provide more information. And in a few days, you will also get the recording of the talk on our social channels and YouTube channels, so to share if you want to with other people. So it was really a pleasure. Thank you again.
Yeah. And have a nice day, everyone, and thank you for your time.
And thank you all for being here, and see you for the next webinar of our series. Goodbye.